Hi everyone. In this lesson, we're going to go over hypothesis testing for a population mean when your population standard deviation sigma is unknown. Now recall that when we performed hypothesis testing previously, when we assumed that sigma was known, that we used this as our test statistic. So this is what we use if the population standard deviation sigma is known. So recall the x bar is our sample mean, mu naught is our proposed population mean, and then we divide that by sigma over root n. Well, now if sigma is unknown, well, we don't know what this value is, so we can't really use this formula. Well, it's a pretty easy modification. All we have to do is replace the value sigma right here. We just replace that value with our sample standard deviation s. So when we take our sample of size n, we calculate x bar, our sample mean. We calculate our sample standard deviation s. And then we just use this formula but with an s in place of the sigma. So this is what we use for our test statistic. So that's what we use when sigma is unknown. However, another change is that we don't use the standard normal distribution anymore. Recall from our discussion with confidence intervals that these values actually follow a student t-distribution. So we have to calculate this value, and then we can use the student t-distribution to calculate a p-value, or we could use the student t-distribution to determine a critical region, and then we see whether or not this value falls in the critical region. If it does, we reject the null hypothesis. So that's how things are going to change when we don't know the population standard deviation. We simply replace the sigma with our sample standard deviation, and then in place of the normal distribution, we use the student t-distribution to calculate a p-value. Now let's take a look at a summary of all this. So right down here we have a table summarizing hypothesis testing when sigma is unknown. So you see you still have two-tailed, right-tailed, and left-tailed tests set up exactly as before. Now your test statistic for each one is the same. It looks just like it did with sigma known, except you notice right here we have a sample standard deviation s instead of the population standard deviation sigma. And then we can calculate a p-value using these commands. Either this one for a two-tailed test, this one for a right-tailed test, or this one for a left-tailed test. So once we calculate these values, we just compare them to the significance level alpha. If your p-value is less than alpha, you reject the null hypothesis. Otherwise, if it's bigger than or equal to alpha, you fail to reject the null hypothesis. Now, alternatively, in place of the p-value method, you could calculate a critical region and then determine whether or not your test statistic falls in these critical regions. Now, the values t alpha over 2, t alpha, and negative t alpha would be determined using the student t-distribution and your significance level alpha, and down here are the commands that you would find for that. Right here and right here. So this command right here would calculate t alpha over 2 if you're using a two-tailed test, and this command right here would calculate t alpha if you're using a one-tailed test. But usually the p-value method is a bit easier to use, so most of the time you'll be using these commands right here. So let's take a look at an example. Now in this example, the McFarland Insurance Company Claims Department reports that the mean cost to process a claim is $60. Now, an industry comparison showed this amount to be larger than most other insurance companies, so the company instituted cost-cutting measures. So to evaluate the effect of the cost-cutting measures, the supervisor of the claims department selected a random sample of 26 claims that were processed last month, and the sample information is reported down here. So here are the 26 costs. Now, at the 0.01 significance level, let's test the claim that the mean processing cost for insurance claims is now less than $60. So that's what we want to set up. We want to set up a hypothesis test for this. So what we're going to do is the following. So we have to identify all of our variables in this problem. So first of all, notice that we have a sample size of 26 that was taken. We also have a significance level of 0.01 that we want to test at. And now let's set up our hypothesis test, our null and alternate. So we're going to set up our null like this. So it's going to be our null that our mean processing cost is still $60, and the alternate is going to be that the mean is less than 60. So the burden of proof here is on the claim that our mean processing costs have been reduced. Notice that we wanted to test that the processing costs are now less than 60, so that's what we set up our alternate hypothesis as. Now, we need to calculate our test statistic, and that's going to require us to calculate X bar. So we'll have to use Excel to do that. And we also need to calculate our sample standard deviation S. And these two will come from our sample data down here. So what we have to do is enter these into Excel or a calculator and evaluate these two here. And then we can calculate our test statistic and our p-value. So let's do that now. Now here we have all of our data entered into Excel. And we need to calculate our sample mean, sample standard deviation, test statistic, and p-value. And then we can determine whether we should reject or fail to reject H0. So our sample mean from our data up here is going to be, using Excel, average. And then I can just highlight these cells right here. So that's A1 to F5. Now these empty cells here will not be included in calculating the average. Excel is smart enough to realize that it will only use cells that have numeric values in them. So as long as we leave them blank, we can highlight the data like this. So there's our sample mean, 56.42. Now we want our sample standard deviation. And we use, notice we use stdev.s for sample. Highlight the data. So A1 to F5 again. Close off our parenthesis and hit enter. And there is our sample standard deviation, 10.04. Now our test statistic, that is going to be our sample mean, which is in cell B7. Minus our mu naught. Now mu naught in this case is 60. Divided by S over root n. So S is our sample standard deviation, that is in cell B8. Divided by the square root of n, which is 26 in this case. And there you go. So notice what we have here is we have the B7 is X bar, the 60 is mu naught, B8, that is S, divided by the square root of n. So there's our test statistic, negative 1.82. Now our p-value, now this is a left-tailed test. So if you look back in your notes or on the formula summary sheet, in order to calculate the p-value, we use this Excel function, equals t.dist. Now we want our test statistic in here, that is in cell B9. Comma, our degrees of freedom. Now our degrees of freedom is going to be 25. That is 26 minus 1. And then we do want cumulative. That's normally what we want when we use the t.dist function as well as the norm.dist. Close that off. And so there is our p-value. Now you will notice that in this problem here now our p-value is larger than the alpha value. So therefore in this case we fail to reject H0. And that is our conclusion. So our conclusion is that the data does not support the claim that the cost-cutting measures have reduced the mean processing cost for this company. Now let's just notice two other things about this problem. If you had used the test statistic and critical region method to determine whether to reject or fail to reject H0, you would have had to calculate the T alpha value, which is given by our formula right here. Notice in your notes. For a left-tailed test, this would be our critical region right here, and the T alpha value can be calculated using this command right down here with Excel. So if we calculated T alpha, we would get this number back. So we use the t dot inverse. Notice we put a negative in front. We want our alpha value, which is 0.01 in this case, and our degrees of freedom is 25. 26 minus 1. There we go. And so our critical region would be this. Our critical region would be t less than negative of this number. This is for a left-tailed test. And so we see, since our test statistic right here does not satisfy this inequality, we would fail to reject H0. If our test statistic had satisfied this, then it would have fallen in the critical region and we would have rejected H0. But this number does not satisfy this inequality, so we fail to reject H0. So you could have done it that way, but most people find the p-value method easier since you can use Excel or a calculator to easily evaluate the p-value. Now let's notice another thing here for this problem. If we had tested at the 0.05 level for this problem, then we would have rejected H0, since our test statistic 0.04 is less than 0.05. So then we would have concluded that the data really does support the claim that the cost-cutting measures reduce the mean processing cost. So in other words, at the level we used, 0.01, that places a rather high burden of proof on the alternate hypothesis, whereas using the level 0.05 places less of a burden on H1. Now, if the processing department suspects that the costs really were reduced, then what they could do is take a sample size larger than 26. And that way, if the population mean really is close to the sample mean of 56.42, say, then your test statistic would be reduced as n is taken larger, and the p-value would decrease. So in other words, if your population mean really is less than 60, then as you take this value right here larger and larger, these values will tend to decrease. Now that is, of course, only if your population mean really is less than 60. Now let's take a look at another example from WebWork. So for this problem, we have that the accounts of a corporation show that on average accounts receivable are $286.16. Now an auditor checked a random sample of 16 of these accounts and found that the sample mean was $294.49, which is larger than this number. And the sample standard deviation was found to be $23.61. Now let's assume that the population is normally distributed, and we want to test the hypothesis that the population mean really is $286.16 against an alternate two-sided test at the 5% significance level. So let's set up our null and alternate hypothesis, calculate our test statistic and our p-value, and determine whether we should reject or fail to reject the null hypothesis. Alright, so for this problem, we have that it's assumed on average that the mean is $286.16. So that's going to be our null hypothesis. And the problem tells us to use a two-sided alternate hypothesis, so that's going to be now our sample of 16 of these accounts had a sample mean of 294.49, so that's our sample mean. Our sample standard deviation was 23.61. And our sample size was 16. All right, so there's all of our information. Now we just need to calculate our test statistic and then the p-value. So if you look back in the formula sheet, recall that our test statistic is given by this. So for a hypothesis test with sigma unknown, this is how you calculate your test statistic right here. So it's going to be x bar minus mu naught divided by s over the square root of n. So for us, that's going to be as follows. So our test statistic t is going to be, well, I'll write it out here for you again, x bar minus mu naught Okay, now our mu naught is the 286.16, so this is going to be 294.49. All right, and then we just have to calculate that number. So that's going to be our test statistic t, and then our p-value. We have an Excel command for that. Now for a two-sided test, recall, let's look back at our formula sheet here. So right here are our choices for a two-tailed, right-tailed, or left-tailed test. For a two-tailed test, this is the Excel command that we want to use. So this value right here, whatever it is we'll calculate that out. That's going to be our t that we put in here. Our n is 16. So for the p-value, we just have to type it into Excel like this: 2 times t.dist of negative the absolute value of this number, and we'll calculate that in a second. 16 minus 1 is of course 15, comma 1, and then that will be our p-value. So let's evaluate these two numbers in Excel now. Now let's just open up Excel and just pick any cell, and let's type in our test statistic right here. Remember to use parentheses correctly. Okay, everything in the numerator has its own parentheses divided by, and then parentheses around what's going to be in the denominator. We'll use the square root command. And there we go. There is our test statistic, 1.41127. Now our p-value, 2 times t.dist of, now I could type in negative 1.41127 here, or I can just do this. I know my test statistic is in cell A1, so I'll go negative ABS for the absolute value of cell A1. Okay, so that'll pull the 1.41127 down into my formula calculation, comma 15, 16 minus 1, comma, and then we always want 1 at the end for a cumulative distribution. There we go. So there's our command. Once again, if you want, you can type in negative 1.41127 right in here. Just remember to take out plenty of decimal places. There is our p-value. So let's write those two down here and then type everything into WebWork. All right, let's go back to our problem. Okay, so here our null hypothesis is mu equals. Our alternate is that mu does not equal. Remember, that's how we type not equal in WebWork. Our test statistic we found to be, and our p-value is. Now, since our p-value right here is larger than 0.05, all right, that is most certainly bigger than or equal to 0.05, we fail to reject H0. All right, so we just have to enter that down here. So we do not reject, click A, do not reject the null hypothesis. And let's check our answer then. Okay, looks like we got everything correct. Okay, so for this problem, once again, just notice that it was assumed that on average accounts receivable was 286.16. A sample of size 16 was taken, and the sample mean of 294.49 was found. That is a little bit bigger than 286.16. However, it is not significantly large enough to reject the claim that the mean is 286.16. That's what we have found here. Okay, so that concludes this web work example.